So on Tuesday, we used mathematical model to illustrate that in the presence of angular dispersion, actually the carrier and the envelope will propagate along different directions, just like this model shows. This is the carrier, which is a pure sinusoidal plane wave. And you can see the mathematical model tells the propagation direction is beta vector direction, which is the propagation constant vector at the carrier frequency. However, A of RT means the envelope function in the time domain. And the model shows the propagation direction is beta prime vector after first order derivative. And it should be different from the beta vector. Just like this equation shows, this is the beta prime vector. It has x component. The magnitude is in green color. It has z component, magnitude in purple color. But beta vector has only z component. It's the reference direction. There is no x component, right? So these two vectors must be in different directions. Okay. So what will happen if this is true? It will result in the phase front tilt with respect to the intensity front. Okay, what is envelope? It's superposition of many sinusoidal waves, right? That will give you the envelope. It travels along beta prime direction, which is shown here. This is the beta prime vector, okay? And the red dashed line represents the intensity front. This is now the phase front. What is phase front? To your knowledge, if you have a sinusoidal plane wave propagating along the z direction, what is the phase front? Set of points, for example, of all sinusoidal peaks. Okay, so certainly it's along the x direction, an infinite planar phase front. But what is intensity front? This is something new. Okay, certainly it's related to envelope instead of carrier, right? So for example, after superposition of many sinusoids of different colors, you got a pulse, right? But on the xz plane, you can collect all the pulse peaks together. That will give rise to your intensity front. And this intensity front, represented by the red dashed line, makes an angle with respect to the blue dashed line, the phase front. And there is an included angle gamma here. Okay? And we have already derived the formulas for beta prime and the beta. This is along z direction. This one has x and z components. So based on the formulas, you can easily evaluate the gamma angle, just taking an arctangent here. Okay. So whenever you have angular dispersion, this is something will happen for sure. Your carrier phase front will be tilted with respect to your intensity front. Okay. But maybe you need to take some time to imagine what does that really mean in three-dimensional space, for example. Okay, this is just mathematical model, simple derivation. You can know the formulas, but maybe you need to think about what would be the picture in three-dimensional space. Yes, please.
Envelope 的 intensity front 跟它的 phase front 有一定的夹角吗？
Yes, gamma. And the gamma depends on these factors, right? For example, your refractive index, ratio of refractive index to group index. This is not 1, right? Because Ng is not equal to N, depending on your material dispersion. So material dispersion will influence the gamma angle. But not just that. You have theta prime, right? Theta prime means angular dispersion. Different wavelengths correspond to different diffraction angle, for example. So this is non-zero, okay? It will contribute to the gamma angle as well. So both material dispersion here and angular dispersion here will determine the gamma angle. Okay. Any other question? But if you have material dispersion but no angular dispersion, what happens? If you have material dispersion, the ratio is not 1, right? But theta prime is 0. And the multiplication with 0, whatever, is always 0. So gamma will be 0. No intensity from tilt anymore. Even you have material dispersion. Okay. But if you have material dispersion, it will further enhance the from tilt. The gamma angle could be larger because of the index ratio. Okay, so keep in mind whenever you use angular dispersive device such as grating, as we will introduce soon, or prism. Okay, this is the accompanied phenomenon. This is always happening. Okay. Now we are ready to investigate the first type of dispersion compensator, the grating pairs. We will start with the model about Tracy grating pair, not just one grating, but two gratings. Okay. And we will evaluate the resulting spectral phase modulation, because this is what we need, right? We need a grating pair to create desired spectral phase modulation. We will talk about the spatial chirp. This is a very realistic phenomenon you have to take into account. Okay? And the varieties of grating pair. So what is Tracy grating pair configuration? Just like this. You have two identical gratings separated by normal distance big G. Okay? And you shine your beam onto the first grating at a certain incidence angle theta I. Okay? Then, if you look at the reference wavelength, lambda 0, for example, the reference ray will be diffracted at diffraction angle theta d. Okay? And you might have known theta d is different from theta I, because this is not just a mirror, it's a grating, right? And the diffracted beam will hit the second grating. And if these two gratings are in parallel with each other, after the second diffraction, the reference ray will propagate along this direction, which is in parallel with the incidence direction. But if this one is tilted, the output ray could be tilted as well. Okay, but usually we need to make sure the two gratings are in parallel with each other. Okay. But we know we are talking about femtosecond pulses. So there are many different colors in the incidence beam, not just one color. This is one color path. So for example, you have a shorter wavelength in blue color. After the first grating, the diffraction angle will be different. Okay, say it makes an angle delta theta with respect to the reference ray at the reference wavelength. So it will hit the second grating at different position. Okay, but after the second diffraction, the blue ray will propagate also in parallel with the incidence ray. Okay, so this is the general picture of Tracy grating pair. Any question? Okay, so in this slide, we define 3 parameters. Big G, which is the normal distance between the 2 gratings. Okay. Small b is the path length between 2 gratings, but only for the reference ray, lambda 0. Delta theta is a function of lambda. It is the angle between the rays at wavelength of interest, lambda, and the reference ray at wavelength lambda 0. Okay, so 3 parameters, G, B, and the delta theta, defined in this slide. But what would be the function of this grating pair? Maybe just like this. You have an upchirp input pulse. What is upchirp? If this is the time axis, higher frequency or shorter wavelength will appear at a later time. Okay? After the grating pair, you can probably arrive at a transform limited pulse. The reason is initially different colors are spread along the time axis. But you can see different colors experience different path lengths in the system, right? So if the path length difference is properly adjusted, after the grating pair, all the colors will propagate together, no time delay anymore. So in the time domain, you have a short pulse, the shortest pulse, or transform limited pulse. So in this sense, grating pair can be used as a pulse compressor, okay? Compressing your upchirped input pulse to a transform limited output pulse. Okay? Yes?
But now you are separating different wavelengths with the space.
Correct. And that would be the spatial chirp we are going to talk about later. If you just use the grating pair in this way, you will suffer from the spatial chirp. Although in the time domain, you compress the pulse, but your beam is adjusted, right? Initially, all the colors might propagate together, but at the output, different colors are spread along different spatial positions. If this spatial chirp is serious, it would introduce some problems for your laser beam. So we need to devise some way to eliminate the spatial chirp. Okay, good question. Any other question? Now, we need some mathematical analysis. Okay. So what we need to derive is maybe the theta d, the diffraction angle, as a function of wavelengths, right? That would be the angular dispersion formula. But how to arrive at this relation? So think about if you have an incidence beam, okay, and ki means the wave vector of the incidence beam. Theta I is incidence angle, So the orientation of ki vector depends on theta I. But the length of ki only depends on the wavelength, right? The magnitude of ki vector is a constant, 2 pi over lambda, right? Wave number, okay? And we assume the grating pitch or period is capital lambda, okay? And after the grating, the wave vector is changed to kd vector, okay? With different orientation because the diffraction angle theta d is different from incidence angle theta I. How about the length? Kd vector's length. Is there any change with respect to ki vector? No change. They have the same length because this is a linear optics, right? Linear optics device. So there is no change of color. If there is no change of color, your wave vector's length will not change. Only the direction can be changed. Okay. And the grating formula, there are different ways you can derive grating formula, but this should be the easiest way. Okay. It's shown here. In physics, it's usually referred to the momentum conservation. But you can also regard it just conservation of wave vector components along the horizontal direction. For example, if this is ki vector, the red one is your horizontal projection of the ki vector, right? And the length is just the k times sine theta I. Okay. For the output ray, the horizontal projection is k times sine theta d. Okay, different. But because of the periodic structure of the grating, there is an artificial wave vector. Here I denote it by k sub m. M is some integer represented in green arrow. Okay. So you can imagine the k sine theta I should be equal to k sine theta d plus or minus kn. If this condition is satisfied, your momentum is conserved. Okay, and then this is what happens here. Small k is the wave number, which is 2 pi over lambda, as we mentioned. K sub m equals m times 2 pi over capital lambda, the grating pitch, right? M is some integer. So if this condition is satisfied, you can easily arrive at equation 11, which is shown here. Sine theta d, which is a function of lambda, equals sine theta I. This is a constant because incidence angle is supposed a constant, times m, an integer, times lambda over capital lambda. So variable lambda is here. That's why theta d is a function of lambda. Okay. Formula is easy, but you might ask yourself why we need to conserve the horizontal projections of the three vectors. We use this condition to arrive at equation 11, right? But why this is necessary? Yeah, I know it's momentum conservation, but why momentum has to be conserved?这跟你力学学到的不一样啊！力学的动量守恒你当然了解，这不是力学啊 ，right？ 这些都是 wave vector only。那当然我们说，假设你有近代物理的概念 ，OK， 光也是 photon，k vector 就是你的 momentum， 所以就把它想成力学的 particle， 那当然也要动量守恒。But I think for most people, it's still not so easy to accept, right? Is there any classical way you can take it? 你不需要用到 photon momentum， 你就可以接受。 this is the right condition.
猫是包含在晶体结构里面传递的 boundary condition 要满足，所以它
There is no crystal here, right?
grating 啊，因为 grating 有那个 Kn，所以它是 crystal，所以它会有一个那个。
Strictly speaking, grating is not crystal, right? It's made by glass. Glass is amorphous, it's not crystal. Grating can be made by different materials. So that's not the key issue. Okay? But you are right, if there is crystal, there is periodic structure, you always see this artificial wave vector. That's right. Diffraction angle is a function of wavelength lambda. Okay, so angular dispersion arises because diffraction angle is a function of wavelength lambda, which is theta d at reference wavelength plus some delta theta. Okay, extra angular change delta theta. If you take first order derivative with respect to lambda for both sides of equality, for equation 11, what will happen? After derivative, you got cosine theta d times theta d prime, right? How about this? After derivative, you got 0 because this is constant. After derivative, you got n times 1 over capital lambda, because this is a linear function of lambda. So after derivative, you got a constant. And by reorganization, you got this formula. Theta d prime, first order derivative, should be equal to n constant over capital lambda constant times cosine theta d. But cosine theta d is a function of lambda. But if you look at this equation, you will see the derivative of theta d should be equal to derivative of delta theta, because this is a constant. After derivative is 0. Okay, so we got the relation, equation 12 here. Delta theta derivative equals n integer over capital lambda cosine theta. Always between minus 90 degrees and plus 90 degrees, right? Theta d is here. Because theta d is always between minus 90 degrees and plus 90 degrees, right? Theta d is here. At most, you can have kb vector along this direction or this direction at most. So this is your angular range of theta d. If you take cosine, because it's the first and the fourth quadrant, right? So cosine theta d is always positive. And according to equation 12, if this is positive, grating pitch is always positive. So you know the derivative of theta d, the sign is always the same as diffraction order n. N is an integer, but it can be positive or negative. Okay, we might need this relation later. Okay, but which n will be used depends on the design of the grating. Okay, sometimes it's designed for n equals 1 or n equals -2. It depends on the design. In theory, every n has some power distribution there. But the designer will purposely make some specific diffraction order extremely efficient, while other orders very inefficient. In that case, we only look at a single n, like -1, if it is designed for m equals -1. Okay. Any question?